Hello everybody. Today's topic is going to be space vector modulation for three-phase voltage source inverters. We have been studying three-phase VSI for a while now. We have started off with square wave modulation and we have discussed both 180-degree mode of conduction as well as 120-degree mode of conduction. Thereafter, we have discussed the sinusoidal pulse width modulation technique, where we have briefly discussed unipolar and bipolar PWM, and I had asked you to draw the waveforms for three-phase unipolar PWM in obviously a three-phase voltage source inverter. Today we'll move on to space vector modulation, which happens to be one of the most exciting topics in power electronics, one of the most conceptually interesting, at least for me. It's one of my most favorite topics in the subject, and I hope that I'm able to convey the concepts of space vector modulation to you to the optimum. So let's begin with space vector modulation. So before we begin with space vector modulation, I'd like to tell you why we even need space vector modulation. If you talk about square wave modulation, which we have discussed earlier, we know that the output voltage of the converter, the fundamental component, its RMS value is around 78% of the input DC voltage, which I have already mentioned to you that it is the highest utilization of the DC available input DC. However, the problem with square wave modulation is that you do not have control over the output voltage, and you have lower order harmonics of the order of 6n plus minus 1 times the fundamental frequency. You try to overcome the problems of square wave modulation by means of the sine PWM technique, where you get control over the output voltage. So you have control over output voltage, and you also have harmonics shifted to the high frequency side. Say JMF plus minus K times the fundamental frequency, which makes it easier for you to filter them by means of the load inductance. So currents flowing through the loads in sine PWM based converters will be sinusoidal, unlike currents flowing in square wave converters. They will have lower order harmonics. But in sine PWM, we saw that we got control over the output voltage and we got harmonic shifted to the high frequency side at the expense of deteriorating the utilization of the DC voltage. So the line voltage RMS value was reduced to only 0.612 times the input VDC voltage. You could of course go beyond 0.612 up till 0.78, that was in the over modulation range, but that was possible only when you were willing to compromise on your harmonic spectrum. So your harmonic spectrum would also have lower order harmonics when you operate in over modulation, and if you want to achieve like exactly 0.78 times VDC, then maybe you'll have to go into square wave modulation and lose control over the output voltage, and of course have all kinds of lower order harmonics in your spectrum. Now today's lecture is going to be about space vector modulation, or the SVM technique, which is popularly known as SVM, space vector modulation, where we basically want that the voltage control over the voltage should be there. We should have control over the output voltage. We should have harmonics shifted again to the high frequency side. In fact, harmonic spectrum should be further improved if possible, and most importantly, we should get better utilization of the input DC. So we want voltages greater than 0.612 times 61.2% of the input DC voltage. So we want to utilize it slightly more. Obviously it's not possible to utilize it as much as 78%, but maybe we can improve from 61% to some higher value. So that we do through the space vector modulation technique. Now let's discuss what space vector modulation is all about. I'm sure you must be remembering from your previous lectures in electrical machines, which I believe you must have had a couple of semesters ago if you're bachelor students, or maybe a year or a couple of years ago if you're master students. So from electrical machines, you know that if you have a three-phase induction machine and you give a three-phase sinusoidal supply to its stator terminals, which is of course which are sine waves and 120 degree apart. So you give a perfect three-phase balance supply to the input of or to the stator of a three-phase induction machine, and you know that the windings are spatially distributed at 120 degrees, which means that in the three phases there is a spatial shift of 120 degrees and an electrical shift of 120 degrees. And in that case, you know that a flux vector is established, a rotating magnetic field is established, which rotates either clockwise or counterclockwise depending upon the phase sequence. But what I mean to say is that due to a three-phase 120 degree electrically shifted supply and given to a set of windings that are 120 degrees apart in space, you can possibly generate a flux vector that is continuously rotating. This same concept of a space vector, a rotating space phasor or a space vector, is used in the control of voltage source inverters. But here we do not talk in terms of flux because there is no flux, unless of course your load is an electrical machine. But for now we are not concerned with the load. We are just trying to generate a three-phase output at a three-phase sinusoidal output at the output terminals of the voltage source inverter. Now if I tell you that the output voltages VA, B and C of the VSI, I want them to be three-phase sinusoidal. That is what is desired or expected from the converter. So I want a three-phase balanced 120 degree phase shifted voltage at the output of the converter, something like this. So when that kind of a supply, that kind of an output is generated at the three terminals of the VSI, then I can associate this output, a sinusoidal output, I can associate it with a space vector. Now how do I associate it with a space vector? Is that I enforce a spatial 120 degree shift to these output line voltages. Let me explain. Say I have three output voltages, Vm sine omega t, and the other is Vm sine omega t minus 120 degrees, and the third one is Vm sine omega t plus 120 degrees. This is the desired output, or you can call it the reference output of the converter, what I desire from the converter, right? Obviously it's not possible to generate exact sine waves, but this is what is desired. So now I desire a set of three-phase voltages at the output of this converter, and I simply add these three up by assigning a space angle of 120 degrees to each waveform, and then I add them up. You must have come across this equation before, which is very similar to the equation of the flux vector in induction machines. So if you add this up, you will get a rotating voltage vector. Let's call it V reference, a vector whose phase is continuously changing from 0 to 360 degrees, that it is continuously rotating, and that flux vector has a fixed length. If you remember from your course in machines, the flux vector generally has an amplitude of 3 by 2, say 3 by 2 or 0.15 if you just simply add these up. Therefore, when I define my space vector here, I define it with a 2 by 3 so that the 3 by 2 and 2 by 3 cancel out, and I get a unity, a vector that has an amplitude equal to unity. It is not necessary to have the scaling of 2 by 3. You may have it or you may not have it. Some books show this 2 by 3, some books do not show 2 by 3. So basically, in space vector modulation, you generate a reference space phasor or a reference space vector, which is simply the space phasor addition of three reference assigned voltages, and you assign them some phase in space. Electrically, you want them 120 degrees apart, and you assign a constant, multiply a constant 2 by 3 to them. So this space phasor these three voltages, when you add them through this equation, it generates a voltage space spacer, space phase, voltage space phasor, which has a fixed magnitude and it rotates counterclockwise like this. So basically, why did we generate this? To simplify our modulation. Why simplify? We have a set of three-phase quantities. We have a three-phase signals, and three signals with some given frequency and some given phase, they can now be interchangeably denoted through one quantity, through one vector. That one vector has a fixed magnitude, and that magnitude is the peak value of the sine wave. That vector has a fixed magnitude and it is continuously rotating. Its speed of rotation determines the frequency of the sine wave, and its position on the circle determines the phase position of the three-phase system. सो बेसिकली जितनी भी इंफॉर्मेशन आपकी सेट ऑफ थ्री फेज सिग्नल्स में है, उस इंफॉर्मेशन को हमने सिर्फ एक क्वांटिटी से रिप्रेजेंट किया, विच इज़ अ स्पेस फेजर रोटेटिंग in a circular path such that it completes one particular revolution depending upon the frequency of the sine wave, and its position, the position of the space vector, it will move from here to here to here to here, and it completes a revolution. Its position at every point is determines the phase of these three phase sine waves, and its magnitude here determines the peak value of the sine wave. So all the information contained in a three phase system is now exactly contained in only one quantity, that is your space vector. अब अगर किसी तरह से मैंने ये रेफरेंस वेक्टर को इमिटेट करने की कोशिश की, यानी कि दिस इज़ माय डिज़ायर्ड आउटपुट फ्रॉम द कन्वर्टर एंड दिस इज़ माय डिज़ायर्ड स्पेस वेक्टर, राइट। और डिज़ायर्ड स्पेस वेक्टर अगर सर्कुलर ट्रैजेक्टरी पे चलता है तो उसका मतलब है कि आपका आउटपुट वोल्टेज का वेवफॉर्म साइनोसाइडल है, विच मीन्स व्हेन यू टॉक अबाउट द स्पेस वेक्टर डोमेन, द सर्कुलर ट्रैजेक्टरी translates to sine waves in this domain, right? And any deviation from the circular trajectory means there are harmonics. That means that it's not a perfect sine wave. So perfect sine waves in this domain, they are represented through a perfect circular trajectory of the space phasor. Now what you want is that using all the switching states of this converter, you have some switching arrangement, some switching states of this converter. Using all these states, you generate the desired reference space vector. Now let's see the possibilities. Now this is your three-phase VSI. You know that in each leg at least one switch has to be on, either S1 or S4. दोनों में से एक को ऑन होना ही होना है, दोनों एक साथ ऑन नहीं हो सकते बिकॉज दैट विल शॉर्ट योर डीसी सप्लाई, और ऐसा भी नहीं हो सकता कि दोनों ऑफ हों बिकॉज दैट विल ओपन सर्किट योर लोड. सो in each leg at least one switch has to be on. Therefore each leg can have at least two states. That means ये on है या ये off है, और ये off है और ये on है. So this leg can have two states, then the other leg can have two states, then the other leg can have two states. So a total of 8 switching states are possible in a three-phase VSI. Now what are those 8 switching states? You can simply tabulate them through digitally tabulate these states. You can have 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So these are your 8 states of the converter, where 0 0 0 means the top 3 devices are off, which automatically means that the bottom 3 devices are on, because obviously the bottom devices are the knots of the upper devices. तो जब भी 0 0 0 होगा तो ऊपर वाले तीनों स्विचेस ऑफ होंगे और नीचे वाले तीनों स्विचेस जो होंगे वो ऑन होंगे. Let's define a reference, a ground point, say let's call it N. and I will measure all voltages with respect to these points, VAN, VBN and VCN. So for the first state, my three voltages are, this is short, this is short, this is short. So the three voltages are 0, 0 and 0. For the second state, this is 0, 0, 1. So this switch is on, this switch is on, and 1 means the top switch is on. So the voltages are 0, 0 and VDC. 0, 0 and VDC. Then you have 0, 1, 0, which means this switch is on and bottom switches are on. So it means 0, VDC and 0. Then 0, VDC and VDC. Then VDC 0 and 0. Then VDC 0, VDC. Then VDC, VDC and 0. And finally VDC, VDC and VDC. So these are all switching states of the converter, and the resulting, you can call them pole voltages if you want to name this point as a pole, and the resulting pole voltages of the converter. This is the only thing that you can extract from the converter. अब इन 8 स्टेट्स के लिए हम देखते हैं कि जो हमारा स्पेस फेजर होगा, लेट्स कॉल इट S or space phasor, whatever you want to call it, let's call it SP, whatever you want to call it, XYZ. हम देखते हैं कि जो हमारा स्पेस फेजर है वो हर स्विचिंग स्टेट के लिए क्या वैल्यू अज्यूम करता है. सो फॉर द वी नो दैट इट इज़ 2/3 times the first output, which is 0, plus the second output at an angle of 120 degrees, plus the third output at an angle of minus 120 degrees. These are the spatial factors, the factors of angular displacement in terms of space that we have forcibly put into the equation to get a space phasor. तो जब आप इसको देखते हो तो इसका वैल्यू what do you get 0. So the space phasor is at 0 for this state, right? Then let's compute for the other state 0, 0, 1. For 0, 0, 1, the space phasor is 2/3, 0 plus 0 at an angle of 120 degrees plus VDC at an angle of minus 120 degrees. So in this case, my space phasor is 2/3 VDC at an angle of minus 120 degrees, right? Similarly, you can go on calculate. I'm sure you can do it. You can calculate for all the switching states, and I would suggest you that you should go ahead and calculate for all the switching states what will be the magnitude and the phase of your space phasor, right? So now let's move to constructing those space phasors. Or constructing the space vector diagram of a 3-phase voltage source inverter. If you construct the space phasor, you calculate the space vector for each of these 8 states, you will see that if this is your origin, you will get this point through the 0, 0, 0 state, and you will also get it through the 1, 1, 1 state. And that is why these two states for the converter are known as the 0 states, because they give you 0 voltage at the output. They give you a 0 position of the space vector. Then if you talk about this state 1, 0, 0, it gives you a length of 2/3 VDC. So this length is 2/3 VDC. And it gives you an angle of 0 degrees. This is the state 1, 0, 0. We had calculated for the state, just now we calculated for the state 0, 0, 1. It had a length of 2/3 VDC and an angle of minus 120 degrees. And this was the state 0, 0, 1. If you calculate for the remaining states 1, 2, 3, 4 हो गई, you will see that they occupy the corners of a hexagon, something like this. So if you calculate for 110, you will find an angle of 60 degrees. If you calculate for 010, you will find an angle of plus 120 degrees. For 011, it will be minus, you can say 180 degrees, and so on. So I would suggest you to calculate for all the 8 states of the converter, the space vector, and you will see that they assume all these positions. 2 positions are occupied at the origin by the 0 vectors 0, 0, 0 and 1, 1, 1, and the remaining 6 vectors take up positions on the 6 corners of a hexagon. If you join this, this is not a circle but a hexagon, which means you transfer this into the 3-phase domain. This hexagon is not going to translate into a sine wave, no, but it is actually going to translate into that quasi square signal or that square wave signal. If you're talking about the pole voltages, it is going to transform into a square wave signal. And this hexagon actually is representing that there will be harmonics in your supply if you simply go on conventionally modulating the converter. But it is very much possible to emulate a circle within this hexagon. Now say how. I generate a reference space phasor, V reference, what I want from the converter as 2/3, what I want as a first pole voltage to be Vn sine omega t at an angle of 0 degrees plus Vm sine omega t minus 120 degrees at an angle of 120 degrees plus Vm sine omega t plus 120 degrees at an angle of minus 120 degrees. This is what I want from the converter. मैंने ये 3 फेज वोल्टेजेस को इस तरह से ऐड अप करके एक रेफरेंस स्पेस फेजर जनरेट किया, और वो रेफरेंस स्पेस फेजर जो होगा, बिकॉज इट्स कंस्ट्रक्टेड फ्रॉम साइन वेव्स, दिस इज व्हाट वी वांट फ्रॉम द कन्वर्टर. It will trace a circular trajectory, something like this. It will go round and round like this, and it will trace a perfect circle because it is constructed from sine waves, perfect sine waves. Now what do you want? You want that using these discrete positions on the space vector diagram that these switches can give you, you want to emulate that circle. So at every point in time, what do? You check the position of the reference space phasor. That is what is desired from the converter. Suppose your reference space phasor is here. Its magnitude is this much, and its phase is something like, say, theta. What you do, you cannot switch it here because the converter does not have a switching state here. But you can use vector addition that you can switch this and this rapidly in such a way that it gives you the effect that your actual phasor is here. So basically you switch this state and then you switch this state such that the resultant is equal to your reference space phasor. And your reference space phasor is not just here, it is moving. The reference space phasor moves from here to here. And then obviously you will have to switch this state for a longer time, and then this state for a lesser time. And you go on moving around this space vector diagram, continuously going round and round, and continuously you calculate your adjacent vectors and for how long do you have to switch them such that you create the effect of tracing a circular trajectory, so that you create an effect that you are tracing points in the middle when you don't even have vectors in the middle. You just trace those vectors by means of simply switching between adjacent vectors rapidly and producing the effect that your vector is actually here when it is not even possible to switch this vector. So इनको rapidly switch करने से at given duty cycles you can emulate the vector position to be here or here or here or here, and basically you create the effect of a sine wave or a circular space vector, which is basically a sine wave in the 3-phase domain. So now This brings us to calculating for how long do we have to switch which vector. Now let me take the first sector. So this was a space vector diagram, which was you could break it up just like a pizza into six cones, or we call them 6 sectors. Let's take the first sector. It is enclosed by the state 1 0 0 and 1 1 0. 1 0 0 means this is on and these two are on, and 1 1 0 means these two and this one is on. So these two switching configurations can give me a space vector at any position in between, at this position. This is the first vector of the first sector of the space vector diagram. At when the space vector, the reference space phasor is in the first sector, आप इन दोनों states के बीच में choose करोगे. What you do at every point in time, आप अपने reference space phasor से जो आपने खुद से sine wave से create किया है, आप उसका theta detect करोगे. तो उसका theta with respect to, you can say, the 0 point. You detect its theta. Say this vector is, you can call it v1, its length is 2 by 3 times vdc, and this vector you can call it v2, its length is also 2 by 3 times vdc. तो आप क्या कहते हो कि v1 को हम t1 टाइम्स के लिए we will switch it, और v2 को हम t2 टाइम के लिए switch करेंगे, such that when we add them vectorially we get the reference vector Vr switched for a total time interval of Ts. That means V1 T1 plus V2 T2 will give you Vr Ts. आप इस V1 वेक्टर को ड्यूटी रेशियो देते हो, टाइम और ड्यूटी रेशियो इन व्हिचएवर डोमेन यू वांट टू टॉक. आप इसको स्केल करते हो बाय मीन्स ऑफ टाइम कि इसको कितनी देर तक देना है, सो दैट टाइम एवरेजिंग करके इन दोनों वेक्टर्स की आप इस रेफरेंस वेक्टर की लेंथ और उसका फेज कंट्रोल कर सकते हो. राइट नाउ every time you have to monitor this theta, and then you can calculate T1, T2 and Ts, where Ts is each switching interval. Ts तो आप खुद से decide करते हो depending upon what switching frequency you want. Now if you see here, this is this is theta. This will be 60 degrees because each sector is a hexagon, so each sector is going to be 60 degrees. So if this is 60 degrees, the inner one is going to be 120 degrees, and if this is 120 degrees, this is going to be 180 minus 120 minus theta. So this one is going to be 60 minus theta, right? So if we apply Lem's theorem, on this, we can simply write the sine rule, what you call the sine rule. This is sine of theta divided by this length, that is V2 T2. That means V2, which has been scaled by T2, is equal to sine of 120 upon VRTS is equal to sine of 60 minus theta upon V1 T1, that is V1 which has been scaled by T1. So what do you do then is that you find the time intervals T1 and T2 कि कितनी देर 100 को switch करना है और कितनी देर, then you find T2 कि कितनी देर 110 को switch करना है. So let's find T1. T1 in terms of VRTS will be sine of 60 minus theta into VRTS divided by V1 sine of 120. Sine 120 को we can write it as root 3 by 2, और V1 को we can write it as, we know that its length is 2 by 3 times VDC, this and this will go, and this will become root 3 over here. So something like this, right? And similarly you can find, अब VDC आपको पता है इनपुट क्या है, VR है कि आपको कन्वर्टर से क्या आउटपुट स्पेस फेजर का मैग्नीट्यूड चाहिए, थीटा है कि वो स्पेस फेजर की इस टाइम पे कौन सी पोजीशन है, यू हैव टू कंटिन्यूसली डिटेक्ट द सेक्टर एंड इस पोजीशन, और उससे आपको मिल जाएगा TS है आपको क्या स्विचिंग फ्रीक्वेंसी चाहिए उसका इन्वर्स, उससे आपको मिल जाएगा कि कितने टाइम के लिए आपको T1 पे स्विच करना है. T1 was the first vector which was 1 0 0 and this one was 1 1 0. तो आपको T1 मिल गया, ठीक. उसके बाद आप देखते हो T2 from the same Lem's theorem, this one turned out to be sine of theta VRTS into root 3 times VDC. अब आपने कुछ टाइम के लिए TS आपका पूरा स्विचिंग इंटरवल है, आपको 10,000 स्विचिंग फ्रीक्वेंसी लेनी है तो इट विल बी 1/10,000, 20,000 लेनी है तो 1/20,000. आपको पता चल गया कि सपोज योर TS कॉरस्पॉन्ड्स टू से 10 माइक्रोसेकेंड्स, सपोज दिस इज योर TS. अब आपने T1 निकाला, इट केम आउट टू बी 5 माइक्रोसेकेंड्स, एंड देन यू फाइंड आउट T2 एंड सपोज दैट केम आउट टू बी 3 microseconds. So 5 microseconds for T1, 3 microseconds for T2. What happens in the remaining 2 microseconds? In the remaining 2 microseconds, आप switch करते हो zero state. Because if you switch T1, it's going to get your vector downwards. If you switch T2, it's going to get your vector upwards. But right now you want this to be the position of your vector, जिस हिसाब से आपने T1 और T2 को कैलकुलेट किया है. और अब आप इस पोजीशन को, ताकि ना ये यहाँ जाए और वहाँ जाए, और TS में जो रिमेनिंग टाइम है उसके लिए आप अपना जीरो वेक्टर स्विच करते हो. जीरो वेक्टर यानी कि 0 0 0, upper 3 devices, all upper 3 devices off and bottom 3 on, of course, or it can be 1 1 1, all upper 3 devices on and bottom 3 devices off. So the zero states are just for balancing your space vector at that position. कि T1 and T2 निकल गए, अब इस position पे इसको retain करने के लिए, see, zero state is going to affect only the magnitude. It's not going to affect the phase. These states are going to affect the phase as well as the magnitude. So once your T1 and T2 have been found out and the remaining time TS, जो TS में remaining time होगा, उस time के लिए आप zero state को switch करोगे so that your vector does not move position. And automatically when the vector, when it has moved position, the reference vector has moved position, उस time पे फिर आपका T1 change होगा, आपका T2 change होगा, और automatically आपकी zero state भी change होगी. Your vector will continuously rotate, reference space phasor, and continuously you will monitor its position theta, continuously you will monitor its sectors, and continuously you find the T1 and T2, the times for which its enclosing vectors have to be switched. So that is the concept of space vector modulation. Now there is some very interesting thing. ये सारा हमने किया, ये क्यों किया? We did this. There are many benefits of space vector modulation. In fact, I would give that to you as a home assignment, that what other benefits does space vector modulation gives you. But one of the most important benefits of space vector modulation over your sine PWM is that it gives you an increased output voltage conversion ratio. जहाँ sine PWM आपको सिर्फ 61.2% देता था output पे, space vector modulation will give you more. Let's see how much it will give you. This is your space vector diagram. ये वो 6 डिस्क्रीट पोजीशंस हैं जो आपको स्क्वायर वेव देती हैं, और इनके बीच में रैपिडली स्विच करने से आप इनके बीच की पोजीशंस को भी इम्यूलेट कर सकते हो, राइट. नाउ दिस इज द हेक्सागन दैट दे एनक्लोज. इन 6 वेक्टर्स को और ऑब्वियसली बीच के 0 वेक्टर्स को यूज करके आप सबसे बड़ी कौन सी सर्कुलर ट्रैजेक्टरी ट्रेस कर सकते हो? अ सर्कल इंस्क्राइब्ड विद इन दिस हेक्सागन. The biggest circle inscribed within this hexagon will tell you the maximum value of the sinusoidal or the fundamental component that you can get from it, right? Now, what is the biggest value of this hexagon? That is the radius of this hexagon. यहाँ पे इसको touch कर रही है, right? What is this value? What is the radius of this hexagon? This value is 2/3 VDC and this is 30 degrees. So the maximum value, let's call it say V max. V max will be V1 or V2 cos of 30, projection of this on this, 2 by 3 VDC, which is length of the vector V1, into cos of 30, which is 2 by 3 VDC into root 3 by 2. This goes, this goes, this becomes VDC by root 3. Now this VDC by root 3 is the maximum peak value. This is the peak value, right? The peak value of the pole voltage. What is the RMS value of the pole voltage? Divided by root 2. And we are still dealing with pole voltage क्योंकि ये सारा space phasor हमने pole voltage के लिए बनाया है. You can construct a space phasor for the line voltage also, that's completely okay. But right now we have made a space phasor for the pole voltage. So for the line voltage, it will simply be multiplied by root 3. So this root 3 goes, this root 3 goes, this becomes VDC by root 2, which is 0.707 times VDC. That is the RMS value of the fundamental component of line voltage. So what did you get? Using square wave modulation, you got 0.78 times VDC. Using sine PWM, you got 0.612 times VDC. Using space vector PWM, you got 0.707 times VDC. So you increased the voltage that you got from sine PWM while maintaining a desired harmonic spectrum, while maintaining a circular trajectory. आप obviously इससे ज़्यादा भी you can go here also, you can exceed the circles, but of course yes, you will not get, you can exceed the circles only at some positions. आपको उससे pure circular trajectory नहीं मिलेगी. That's going into over modulation, even with space vector modulation. But remaining within the boundaries of sine wave, you can get 0.707. If you say divide 0.707 by 0.612, that is 1.15. That means you're getting more than 15% of voltage you have increased from sine PWM just by the use of space vector modulation. इनफैक्ट ये चीज़ जो है ना, ये लेंथ ऑफ द वेक्टर यहाँ पे पूरा ये किसके बराबर है? 2/3 VDC के बराबर है. अगर आप 2/3 VDC आपकी पीक पोल वोल्टेज है, ये स्क्वायर वेव में है, दैट इज़ यू divide it by root 2, it will give you RMS pole voltage, and you multiply it by root 3, it will give you the line voltage. So this root 3 becomes here and this becomes root 2 over here. This should be root 2 by root 3, it should be 0.78 VDC. मैंने आपको इस पूरे वेक्टर की लेंथ के हिसाब से बताया क्योंकि that is what you get in स्क्वायर वेव मॉड्यूलेशन. ये 0.78 के बराबर ही होगी. मतलब व्हाट कैलकुलेशंस वी हैव डन फॉर 0.78 VDC फॉर स्क्वायर वेव मॉड्यूलेशन, यू कैन इवन सी इट विजुअली एंड डू इट यूजिंग द स्पेस वेक्टर डायग्राम ऑल्सो. दैट्स व्हाट आई एम ट्राइंग टू टेल यू. बट बिकॉज यू वांट टू चेक ओनली फॉर द साइन वेव पार्ट, तो आपको इसके अंदर का सबसे बड़ा सर्कल जो इंस्क्राइब होगा cos 30 पे, उसकी लेंथ देखनी है और उससे पता चल रहा है दैट यू कैन यूटिलाइज योर DC ओनली अप टू 70.7%. So what happens now? अब हम सपोज पहले स्पेस फेजर में हैं, पहले सेक्टर में है जो एनक्लोज हो रहा है 100 से और 110 से, और हमने देखा कि इसको T1 टाइम के लिए कहीं पे आपका स्पेस फेजर है इस टाइम पे, उस हिसाब से आपने T1 यू हैव कैलकुलेटेड एंड यू हैव ऑल्सो कैलकुलेटेड T2. And then remaining time interval is supposed to be T0 when you have to switch the 0 state, that is 000 or 111. Even while making these switchings, you have to carefully distribute the switchings so as to maintain waveform symmetry. Now tell me why. The first state is say 100, we're talking about the first sector, and the second state is 110. And then you can have a 0 state which can be either 000 or 111. आपके पास इसका टाइम भी है T1, इसका टाइम भी है T2 और इसका टाइम भी है टी नॉट, लेकिन इनको एक ऑर्गेनाइज्ड सीक्वेंस में स्विच किया जाता है सो एज टू मेंटेन वेव फॉर्म सिमेट्री. और स्विच ऐसे किया जाता है दैट वंस यू गो फ्रॉम वन स्टेट टू अनदर यू डू नॉट कॉज मोर देन वन ट्रांजिशन. लेट्स सी हाउ. फर्स्ट यू स्विच 0 0 0, दैट इज योर ज़ीरो स्टेट. फिर उससे आप 1 0 0 में जाओगे, यू कॉज ओनली वन ट्रांजिशन. फिर इस स्टेट से आप 1 1 0 में जाओगे, दैट इज अनदर ओनली वन ट्रांजिशन. फिर इस स्टेट से आप 1 1 1 में जाओगे. फिर इस स्टेट से आप वापस 1 1 0 में जाओगे. देन अगेन यू विल हैव go back, you will have 1 0 0 and then again you will have 0 0 0. और ये पूरा आपका एक TS कंबाइन करेगा, यानी कि जितना आपने T1 से, दिस इज T1, जितना आपने T1 निकाला था आप उसको T1/2 में डिवाइड करोगे. T1/2 विच विल स्विच हेयर एंड T1/2 यू विल स्विच हेयर. देन दिस वॉज योर T2. T2 जो आपने निकाला था उसको आप T2/2 में स्विच करोगे और 1 1 0 अगेन हेयर, इसको T2/2 रिमेनिंग T2/2 को यहाँ पे स्विच करोगे. और जो आपकी T नॉट है उसको आप T0/3 में स्विच करोगे. वंस यूजिंग 0 0 0, अनदर टाइम ऑल्सो यूजिंग 0 0 0 एंड सम वंस इवन यूजिंग 1 1 1. तो आपने इसको 3 इंटरवल्स में स्विच किया. नाउ यू विल आस्क मी वाई. आई विल शो यू वाई इन अ वेरी सिंपल वे. हम वोल्टेज ड्रॉ करेंगे VAN, VBN एंड VCN. जब 0 0 0 होगा तीनों स्टेट्स, तो आपकी अपर वोल्टेजेस जो हैं, अपर स्विचेस जो हैं, 0 होंगे. बॉटम ऑल 3 स्विचेस विल बी ऑन, सो ऑल 3 पोल वोल्टेजेस विल बी 0. सो दिस इज 0, this is 0, let's draw it with a black pen. This is 0, this is 0 and this is 0. फिर जब 1 0 0 हुआ तो this state becomes high, other two are bottom ones are still low, so the first VAN becomes high and others remain at 0. फिर 1 1 0 हुआ तो ऊपर वाला भी हाई हुआ, ये वाला भी हाई हुआ, और ये वाला फिर भी 0 पे ही रहा. फिर 1 1 1 हुआ तो यू रिमेन हाई हेयर, यू रिमेन हाई हेयर एंड यू गो हाई हेयर. फिर 1 1 0 हुआ तो यू स्टिल आर हाई, यू स्टिल आर हाई बट यू गो लो. Then this remains high, this goes low and this remains low. Finally you goes low, go low and go low. If you observe this waveform, there is symmetry in this waveform. This is high, goes low, then this is high, this goes low, this is high and then this goes low. अगर आप इनको सिर्फ ऐसे डिस्ट्रीब्यूट करते 0 0 0 1 0 0 1 1 0 तो आपकी वेवफॉर्म में सिमेट्री नहीं रहती. Do you see that? There was no symmetry in this waveform. But because you have split these timings, you split them in such a way that you cause only one transition. In fact, ये एक transition वाली चीज़ आपको इसमें भी help करती है, आपके switching power losses कम होते हैं. एक तो switching transitions कम हो गए. Every time you switch, only one device has to change its position or change its state. Another thing is that you're maintaining waveform symmetry in the 3-pole voltages, so that gives you an improved harmonic spectrum. So space vector modulation overall gives you a better harmonic performance as compared to sine PWM if you organize or distribute these dwell times. You call them dwell times, DWELL, कि हर स्टेट में कन्वर्टर को कितनी देर ड्वेल करना है, कितनी देर रहना है. यू फाइंड दीज ड्वेल टाइम्स T1 T2 and T0 and you distribute these dwell times. Sometimes people even distribute them by 6 or by 8 or by 4 depending, just to improve the symmetry of the waveform and to make it, जितनी ज़्यादा symmetries आपके waveform में होती है उतना अच्छा उसका harmonic response होता है. So this is one of the basic ways of distributing these dwell times so that you get waveform symmetry. So this was about space vector modulation. It gave you increased voltage conversion ratio from 61.2% to 70.7% just while maintaining your sinusoidal output, while maintaining a good harmonic performance. Second, you can rearrange your dwell times in such a way that you get waveform symmetry and therefore you can increase the harmonic performance further. So the basic concept behind space vector modulation was to use the concepts that we had already developed in machines to generate a fictitious quantity, that is the rotating space phasor of voltage at the output of the converter. आपका reference vector कैसा है, वो sinusoidal quantities से वो एक circular trajectory trace करेगा, लेकिन फिर उन्हीं switches को use करके, वो discrete combinations of states को use करके कैसे आप एक circular trajectory को emulate करोगे, that is the concept of space vector modulation. So basic mathematics, simple geometry, simple Lemaire's theorem of, and then algebraic sum of quantities, and then simply emulating a circle using 6 discrete positions of a space vector diagram. If it's not very easy for you to understand it in the first go, I understand many people find it difficult to study and understand space vector modulation. It was just a humble attempt. I'm not sure if I've been able to deliver my best, but you can always come up with your questions and you can always do some extra reading. It's a very interesting topic, and I'm sure if you have the time and if you try to implement it for a 3-phase voltage source inverter, things will be clearer to you. So wishing you all the best. Keep me posted if you have any questions or queries.